Yeah, thank you, Michael. So, wonderful to see so many people interested in mathematical programming approaches for optimal university timetabling. This is the title of my PhD, and it's also the agenda for today, so to speak, in reverse order. We'll start by talking about timetabling, or we'll look into timetabling. What is timetabling? What is university timetabling? Why is it interesting to do research in, not least? And what do we mean about optimal university timetabling? What is optimality? How do we measure it? And why do we think this is important to do optimal university timetabling? And then we will slowly go through the mathematical programming approaches that I have applied within the last 3 years to this problem. Finish off with a few notes on how we can improve this research in the future. Yes. As he mentioned, it is an industrial PhD, so it has been performed as a collaboration between MACOM and a research group here at DTU called More Time. And then it's financially supported by the Innovation Fund Denmark. And MACOM is a software provider for the educational system. And the majority of their customers today are Danish high schools. And what they deliver is a cloud-based system for administrative tasks, document sharing, communication, and timetabling. That's one part, a very, very small part of the software, but it's there, and it can deliver automated timetabling for the high schools. And this is why they have an interest in this project, because they also want to move into the university market as well. This is an example from the webpage lecture.dk. This is where this is their system. I've just clicked into the webpage. You don't have to log in. I just pick the school and a room. And here we can see which events are going to occur in this specific room this week. So this is what we mean by timetabling, scheduling events at specific times. For the high schools, this is classes, it's exams, it can be parental supervision, and many other problems. And the problem, what you also can see is that at any point of time in this room, we have no events overlapping. This is because we cannot have, for instance, one teacher teaching math and another teacher teaching history in the same room at the same time. It will be confusing for the students to listen. I don't know many humans that can actually do this and understand both lectures at the same time. And also, the teacher cannot teach 2 different lectures at the same time. Even though you might have a very good math and physics teacher, he cannot both teach math and physics at the same time. This will also be a bit confusing. And furthermore, a student cannot be physically present for 2 different lectures at the same time. It's a physical restriction that we cannot just deal with. These are conflicts, we say. If 2 events are taught by the same teacher or attended by the same student, we say that they are conflicting with each other and we cannot schedule them at the same time. This is the core of timetabling problems. Scheduling events at the same time and ensure that the events are not conflicting. So for university timetabling, it's just timetabling at universities. It's more or less the same. Now we're just dealing with courses instead of classes, but still with exams as well. And this problem, as I said, is interesting for MACOM because they want to move into the university market, and many universities here in Denmark are complaining about the timetables and the planning process in doing it because they're all doing it manually, as opposed to the high schools that are actually doing it automatically today. So they are a bit behind here. From that perspective, this is an interesting point of view from MACOM because they can get into the universities. From academia, it's interesting because the problem is really, really, really hard. And to drive research more into this field, a competition was created in 2002 where researchers could work on the same problem specification, same data sets, and compare results with each other. This made the problem very popular. Well, it was researched before, but it made it even more popular after the competition, because now we had the same data set, the same problem we could compare with each other. And because it's extremely hard. It was such a success that 5 years later, a new competition was created again. And one of the main contributions was not to just consider university timetabling, but to specify different problems within university timetabling. And one of the main areas they divided the problem into was course timetabling and exam timetabling. One problem, your events are courses, and you need to find out when your courses should occur and in which rooms. And the other one is exams instead of courses. So almost the same, but they split the course timetabling into further two parts. One named curriculum-based course timetabling and the other post-enrollment-based course timetabling. One of the main differences is that the curriculum-based course timetabling problem is solved before the semester starts, before the students enroll for the courses, so we do not exactly know which courses the students are attending. And this is one of the headaches here in Denmark at the universities, that they are trying to schedule all the courses before the students actually enroll for the courses. So this has also been the focus area in this PhD thesis, because it's most similar to the problems we know here in Denmark. In the competition, 21 datasets was published. So you will see a lot of literature which are focusing on solving these instances to compare with each other. And we're also using these instances so we can benchmark towards other researchers, but also because it was really, really hard for us to get data from the Danish universities. They are, slow. As I said, a bit behind the high schools. Yeah. You see the next slide? Yeah. So the question is, why is it so hard? For those who do not know about the problem, the reason it is hard is because in its core, just finding these timetables, making the timetables work, is a graph coloring problem. And for those of you who know complexity theory, you know this is a hard problem. For those who do not know complexity theory or graph coloring, this is a graph. The circles, we call them nodes, and the edges are called, the lines are called edges. And the graph coloring problem is then to color these nodes. Every node needs exactly one color. For instance, I can color this a very, very dark green. And if I have two nodes connected by an edge, I cannot assign them the same color. I'm not allowed to do that. And the idea is I have a limited number of colors, and I need to color the entire graph such that this property holds. And in general, this is a hard problem. Very, very hard. It's one of the hardest problems we know in math. And the relation to timetabling is that the nodes represent events. And the edges between events are if events are sharing resources, if they're taught by the same lecturer, or the same student is following both courses. And the colors then corresponds to the specific times that we're assigning the courses or the events. So instead of having a blue color and a red color, we have Monday morning and Tuesday afternoon. That's the relationship. But we are not just striving to find any solution. We want an optimal solution or a good solution. And to find out what is a good solution, well, that varies a lot. Can we do it black? No. Okay. That varies from, of course, institution to institution and individual to individual, but we have these standard benchmarking sets where we can say compare timetables to each other. And to be able to compare timetables, we have to be able to quantify the quality. What is a bad timetable? And what we do is we assign a penalty if we think a solution is bad, a timetable is bad. For instance, we did not have enough seats for everyone in here. That would be considered a bad timetable. So for every person that had to run and get a chair, you would add a penalty. And then some teachers may not like to teach Monday morning from 8 to 10 and then again from 5 to 7 in the evening. That would also be considered a bad timetable. And then we create some penalty score for each of these undesired traits on the timetables that we do not want. And numbers can be compared. So every timetable is just represented by a number. And those are easily to compare. So what we're striving to is to lower this number. And if we look into the literature, how is it done? Who are the usual suspects when we look into literature? And what we see is that the literature is very heavily dominated by heuristics. Heuristics, usually a very common way to approach the problem is to generate a feasible timetable and then maybe improve that timetable by making some small changes or something like that. So you will get some score on the solution and then you will improve it and try to further on improve. The question is, when can you not improve anymore? At some point you will reach the optimal solution, and the drawback of this heuristics is that they don't know. They only know the timetables they're in, they only know what the value of the solutions are. So he's a timetable, he's a heuristic, and he's a heuristic, and he's a heuristic, he's a heuristic. But there's one guy that knows just slightly more than the others. He has more information. This guy, he is what we call a mixed integer linear programming. We have a few of those. And they look something like this. So he formulates the problem using variables and equations. That's his take on it. And he, just as the heuristics, he do not know what the optimal solution is. But what he can say is, okay, I don't know the optimal solution, but I can compute a lower bound. I can say it's definitely not going to be worse than this value. Then he's going to push the lower bounds up and the upper bounds down, and hopefully they'll meet and he has found the optimal solution. I'll just take this off so I started to sweat. And these are also approaches that I've used the last 3 years, approaches based on solving such a model here. And here it is. So here we have the problem I considered, and all the different methods I tried, I've categorized them into 5 different categories, more or less. It may be misleading that one is called mixed integer programming, because they're all based on mixed integer programming. But what I mean here is this. I just formulated a model like this. I put it into a solver, a commercial solver that can solve such models generically, and then look at the solution. And the others are more advanced methods, because the solver usually are not able to solve these models, so it needs some help. And for each of these groups, I then tried 3 different methods or formulations or implementations of different algorithms. In total, about 15 approaches. Well, it was actually a little bit more, but it looks nicer when it all goes into 3. So let's go through them all. We'll start with the first. No. 4 of these were successful. 4 of these resulted in articles. The rest were not satisfactory for me to start spending time on writing. But for those who are interested, I have one chapter dedicated to that goes through the theory behind all of these methods, why I thought they were a good idea, and what further research can be done in these fields, maybe apply them to other problems or such, just to inspire the research. And today we'll just talk about the 4 that actually worked. We'll start with the top one, flow formulations. I'll get into what that is. Then doing something called Bender's decomposition, where we exploit some network structure in the problem. Then we go on to an extended formulation, a pattern formulation, which we then make a Danzig-Wolff decomposition on. And I assume you know these methods. So, yeah. Otherwise, there's a brief introduction to each method in the PhD as well. Yep. So let's look at the curriculum based course timetabling problem. When we formulate these mixed integer programming models, what is very intuitive and common to do is to have a binary variable for each course and each period and each room. So the number of binary variables in your model is going to be the number of courses times the number of periods times the number of rooms. And it becomes difficult to solve. So a very frequent technique is to split the problem into two parts. One where we only look at the time schedule. We only assign the times, and we do not care about the rooms. They are non-existent to some extent. So we just solve the time problem. We then, when we have solved this problem, found a solution, we put it into some other model that will then, or algorithm, that will then assign the actual rooms that the event should take place in. And sometimes this process is iterated, because maybe the solution from the time schedule makes the room assignments infeasible, so you would have to go back and change your time schedule. But it could also just be because you want to further on improve the solution, because even if you solve the different parts to optimality, you cannot guarantee that your overall solution is optimal. Yes, and I think to get to optimality is important because, as I said before, we do not know when the heuristics are done. I haven't seen the best solutions for these 21 datasets from the competition being improved over the last 4 years. I don't think it's because people are not studying them anymore. Maybe it's because solutions are so good, so it's really hard to improve them. So now we need to work in from the other direction as well. We are inspired by this, but we're not doing this. So we still think of the problems as two parts. A time scheduling problem that does not know anything about the rooms, and then a room allocation problem that does not know anything about the time. And the question is, if I find a solution for each of these models or problems, is it possible for me to combine the solutions into a feasible solution and overall? This is where we use flow models for, that we can show that we can connect the two models by flow formulations. We have two different flow formulations. I will briefly describe one and just mention the other, because it needs more attention. So what we do is, say we have a solution from each of these problems. We create a graph. So we are creating a graph network, and for each course we have a node. And I should say this graph is for every period in our data set that we are constructing this graph. So for each course we have a node. For each room we have a node as well. And then we connect, for instance, take a course, connect it with an arc going to every possible room, and we set the capacity to 1 if the course has been assigned to the room in the room allocation problem. Otherwise, we set it to 0. And we do this for all course and room pairs. We then add a source node with an outgoing arc to every course. And since we are considering a specific period, this graph only, so we are constructing such a graph for every possible period, we set the capacity to 1 if we have assigned the course C to period P and 0 otherwise. This is what this variable is denoting. So we have a bit of math. And in the sink, we have a sink node where every room has an arc going to where the capacity is 1 to simulate that, because we're considering 1 period, that at most 1 lecture can be scheduled in every room. So the flow problem here will correspond to actually taking the time assignments and putting them into the room assignments, or the room problem. So if I send flow from a course C to a room R, it means I've scheduled the course in that room at that specific period that this graph is created for. Now this means I have some flow variables when I'm formulating the model. I have a flow variable for each course and each room in each of these graphs that I have for each period. So again, I have, you could say, a binary variable for each course and each period and each room again. However, the flow problem has this nice property called the integrality property, which means that we do not need to require in the integrality requirement in our model. We can formulate it as an LP, for those who know MIPS and LPs. And what we simply then do is, now we have the time schedule model, the room allocation model, and now we have a flow model in between. We just add all the models together. So we have a model which is as big as when we only considered. No. Where did I put it? Oh, yeah. Yeah. So the model is as big as before when I said that it's intuitive, the intuitive model to generate a binary variable for each course, period, and room. But most of them are continuous, these variables. So we have a very small x vector here, and the y vector is larger. And usually in the test sets we've checked, it's about 10 times the size. 90% of the number of integer variables is 10 times less in this model than in the first model. And then the multi-commodity flow problem is very similar. We're doing the same tricks, so I'll not go through this. But what we see is I have 4 data sets from this competition where the lower and upper bounds still haven't met yet. So all the best solutions that has been created in all the articles, all the best lower bounds that has been created, they haven't met yet. And one of them, we improve the bound by 42%. The question is it because of the reformulation of the model, or is it because the solvers today have improved a lot? Because many of the results are from before my PhD, so they are 3, 4, 5 all the way back to 2007 years old. And the solvers has improved a lot since then. But we compared it to the intuitive model, and here we saw it was a big improvement. So all the other methods, I guess, could benefit from this formulation as well. But this is not what's nice about the problem. What's really, really nice about this formulation is that we have this large number of continuous variables and small number of integer variables. And when we have problems like that, there is one method that comes to mind that is beneficial for such models, and it looks like Bender's decomposition. Yes. I did not practice with this. So this is called Bender's. I'll just get closer so you can see. What we do is we take all these continuous variables that we have, which are the majority of our variables, and project them all out and replace them by constraints, basically, in Bender's decomposition. So now we can see we only have the x vector, the integer variables, and the rest are just constraints, which is a good idea. The problem is that we need exponentially many constraints, so we cannot just enumerate them all. And this is where Bender's in the 60s, he developed a very great method called Bender's algorithm. And what you do is you only add maybe few of the constraints, maybe none of them at all. Then you solve your problem. You call it your master problem. This model here is the master problem. You solve that model. You take the solution, and then we put it into our flow model. The flow model is the variables that we projected out. And what we then do is, given this, the solution, the time schedule, and the room allocation, solve the flow problem, and if it's infeasible, then we have, it's called a dual ray, that tells us that there is a constraint that is violated in our model, in our master problem. So we take this constraint and put it into the master problem, what you can see here, and we iterate. And we keep going until we don't generate any more constraints. Yeah. This is a wonderful solution, I think, and it helped a lot on the lower bounds. We can see we move the lower bound from 42 to 47% for this one instance. But when we compared the method with just the flow formulations, we could see that it actually improved all the lower, or most of all the lower bounds. It had a big improvement in terms of lower bounds. In terms of upper bounds, unfortunately, the solution is not so great at the moment, because currently we're only generating feasibility because the extreme rays of the problem. So whenever the model finds a solution to the master problem and says, oh, give it to us, and say, is this feasible? We say, no, it's not. And it has to cut it away. Whenever it thinks it has found a solution, we reject it, so to speak. So we had to develop some heuristics to repair the solutions. And the heuristic is not good enough to outperform others. But where the real improvement comes is when we look at larger instances. We have a data set from a German university, which is much larger than the data set from the competition. And here we had improvement both on the lower and upper bounds compared to just solving the original, flow formulations. We could push the lower bounds on all the instances up by approximately 40% on average, and the upper bounds we could decrease them by 35%. And this shows that this method is much more scalable than having solving the entire model with a MIP solver. So this was the flow formulations, and now this was actually 2 of the articles we've gone through. Now we will go through the next 2, where we only focus on the time scheduling part. And the problem that we only focus on the time scheduling part is that we see in literature that this is where the most problems are, where it's really, really hard to solve the problem. And if you solve this problem only, create lower bounds for this, you also get lower bounds for the overall problem. So in our strive to improve the lower bounds, it makes sense to put attention here, because it is so hard. And currently, we had the time scheduling model scheduling courses to periods, so we have a binary variable for each course and each period. And what we do now in our last methods is to replace them. Now I'm going to over there. Yeah. Here I have a more or less general, it's going to be hard to see, yes, a more or less general formulation of the Danzig-Wolff decomposition. Now in the article of the first article of the last 2 articles, we do not mention it's a Danzig-Wolff decomposition, but in fact it actually is. And both of the last methods are Danzig-Wolff decompositions. But so what we do is, instead of having one binary variable for each course and each period, we are going to look at all the different combinations that you can do on one day. So let's say our day is divided into 3 time slots, and it means that there are 8 different possibilities. You can assign a course to a day, when it should be. Should it be just in the morning, or should it be all 3 time slots? And now we have a binary variable. Instead of for each course and each period, we have for each course, each day, and each possible combination that the course can be assigned to this day. So it's a much larger number of variables. It's exponentially large. Luckily, what we see, for instance, here we only have 3 or 8 solutions. When we have 4 time slots, it's only going to be 16, which were the case for the Macom timetable I showed you. And for the instances from the competition, it's usually 5 or 6 time slots the days are divided into. So it's only 64 different combinations we have. So we can enumerate them all. And then we simply just replace the entire model with patterns instead of. What I now do here is that I took all those 21 data sets and I took the original formulation and then I made this, replaced them by these patterns and just solved the LP relaxation, because we know this is the bound that the branch and bound algorithm gets its bound from, is the LP relaxation. And what we see is when we do this pattern formulation instead, the lower bounds are the same. So we're not getting anything from doing this right away. But the patterns, they have one specific property that makes them beneficial that the compact formulation does not. It's possible for us to take a specific course, a specific day, and a specific pattern and say, is this combination ever going to be in any feasible solution, yes or no? We have a lot of different pre-processing tricks to eliminate many of the variables from the model. And then when we solve the LP relaxation after this, we improve the bounds. Now we get, well, significantly better bounds than the compact formulation. And we have another helpful, it can provide us with more help. We can generate valid inequalities that would be harder for the compact formulation. Here I have a graph, so we're still networking a bit. I have a graph where I have a node for each variable in my pattern formulation, and an edge between 2 nodes if those 2 variables cannot be in the same solution at the same time. There can be different reasons for this. Basically what we're doing is using all our pre-processing techniques where we just considered 1 variable at a time. We do the same, now we're just considering 2 variables at a time to generate these edges between. And then we can say, okay, I have these 3 variables here, for instance. This is a clique. None of these 3 can actually be in the same solution. This is a clique inequality, so we can sum them together, the variables, and say they should be less than or equal to 1. This is standard for timetabling and stuff, so many of you have seen it and know it. But we can get much stronger constraints from the pattern formulation than from the compact formulation. And we also have a clique here and a clique over here. What we do is we enumerate or create a lot of these cliques in this graph such that we ensure that every edge in the graph is going to be in at least one of these cliques. And then we just get slight improvement, but only for some of the solutions. So from the LP perspective, it's maybe not that beneficial. It takes a long time to actually do all this, creating this graph and all the edges and stuff. But what we see is that the pre-processing tool of the solver we're using can discard way more variables when we have added these valid inequalities than when we didn't. So overall, it gives an improvement to the branch and bound algorithm when we run the full shebang. And now we see an improvement on some more lower bounds, and we add an additional improvement to this bound, so it's in total is a 75 improvement compared to before I started the PhD. Yes. This was the third article. The fourth article is also a Danzig-Wolff decomposition, but now we are making a Danzig-Wolff decomposition of our Danzig-Wolff decomposition. And so it worked fine to create these patterns for each course and each day. But what if we consider an entire week instead? So we created a pattern for an entire week instead. Or take an entire day and say, how should we schedule all courses and create patterns for this? To see which one is probably good. It's not my idea or the first time it's done before, but it's usually been done on the compact formulation, this decomposition, and now we have a stronger formulation, so why not try it on this one as well? And if we take the constraint matrix of our pattern formulation and plot all the different non-zero entries, or every dot here is a non-zero entry in the matrix, and sort them by the columns and the rows by courses, this is the structure we get. So every little square or rectangle here corresponds to all the constraints related to one single course. And for the days, it will look like this. So what we see is we have a much more nicely block angular structure that those who work with Danzig-Wolff decomposition know this is a really nice feature for a problem when we need to decompose. So I actually tested both of them before I did this visualization, and I saw this was way underperforming compared to this, and I didn't really know why, and because it was easy for me to do it, but I think this could be the reason. And if you look into the literature, what most write is that you want most of your constraints into these block angular structures, because okay, it's difficult to explain without. Yeah, you want most of the majority of your constraints down here. This is going to help you most, and we do not have that as much in the course decomposition as in the day decomposition. The problem is, however, the number of variables is extremely large. It's exponentially large. We cannot enumerate them all as we did before. So what we do is we do not contain all the variables in our model. We only consider some of them in our model, and this is then called the restricted master problem. We then solve the LP relaxation of it, get the dual solution from that, which we then put into the subproblem. In this case, if we use the day decomposition, the subproblem is to select which courses should choose which patterns on a specific day, given the dual solution. And then we look for a column which can improve our master problem. If we find such a column, we say they have a negative reduced cost. It's just a bit technical, but we put it into the master problem, and we will iterate this process again and again. I did it, and here is the running time of doing the column generation on these 4 instances, and especially one we see takes a very long time. This is just the column generation to generate all the columns, to be sure that we have all the columns to solve the LP relaxation of the restricted master problem. So it takes a long time, but fortunately, we can improve it a bit. We are doing some pre-processing. I'm not going into details with that because it doesn't give actually much improvement in the pre-processing, I found out afterwards. But what really helps is to consider the problem a bit more smart, or develop some solution strategies for it. And one we use is local branching. So let's, just to explain what local branching is for those who haven't seen it, let's say that this slide here is the solution space, and every point is some solution. Local branching will then take one solution, for instance this one, add a constraint to the model, so you restrict the solver to only consider a subset, just like heuristics do. And then you've tried to optimize only this subset of the entire solution space. And you might get a solution which is better. The optimal I'll just found here. Then you add a constraint saying that this solution space should not be part of the solution space anymore because I've searched it. There's no reason to search it anymore. And you add a new constraint around this new improved solution. So you restrict again the solver to only a small part. And you continue doing this. At some point you cannot get any more further improvements. You then find a new solution and will continue until you have cut away some parts. You will have improved solutions, hopefully, but what you may have improved solutions, but what you will have is a smaller solution space to search for your solver, which you can then put into a solver. So how does this relate to our problem? In the sub-problem, the pricing problem of a column generation algorithm, we're looking for solutions that are negative in value, and solutions we have generated previously in other iterations of our column generation algorithm, many of those will have a zero cost, specifically the ones that are in basis of the model, of course, which is very close to negative, right? Zero is as close you can get to negativity as you can without being negative, actually. So we use those solutions as the inputs to our local branching strategy. And now we get from 81 hours down to 28 hours. So it improves a lot, but it's still a long time to solve a single problem. So we need more research on how we can improve it even further. And also, why is this particular problem so hard compared to the others? Are there some specifics about the structure, about the problem? I haven't looked into it enough, unfortunately. But this is where research is needed. But nonetheless, we improve the bounds further on all the last or the open instances. And now this also get into the race. Overall, the last 3 years, what have they given us? When I started, the average gap on these solutions, these 4 solutions, was 32%. And the gap, by that I mean the best lower bound we have found in the literature so far, and the best upper bounds that has been found in literature. What is the distance between these 2 values? That was 32% when we started, and the worst one, that was this data set which took a long time, was 66%, which we have now improved to 11 and 16%. So we have closed the gap a bit without looking at solutions at all, just by improving lower bounds. We haven't created any new solutions. And this is why I think it's important to research more on the lower bounds, because I think there is more to gain here. And to be able to see if we can validate if the current best solutions we have, are they in fact optimal? We don't know if we don't get better bounds. So what did we talk about today? If you don't remember, we started with the curriculum course timetabling and looked into this split of the problem into 2 sub-problems, which is very common in practice. And one article considered combining the 2 so we can guarantee that the optimal solutions will be found if the solver is given enough time, but usually cannot. We exploited the structure for a Benders decomposition, but what I talked about was that the heuristics to create solutions was not good enough. It's much worse than the entire model, and this is because the solver will lose some information that it cannot exploit when its heuristics is finding solutions. So we need more work on getting better solutions for this method to be really beneficial. Then we looked at the pattern formulations for only the time scheduling part, which we decomposed using Danzig-Wolf. The pricing problems are very hard, especially for some of the instances. We need more research on why are they hard, those specifics. Is the pricing problems correct? Maybe we should make them slightly different to be able to solve them actually. But at least we need more focus here. And I hope in the end I will be able to do it and combine the Danzig-Wolf decomposition with these Benders cuts so I can create a branch cut and price solver that will solve any curriculum-based course timetabling problem in the world. That's my goal. I'll see if I can make it before I die. But and I also think that it could be nice to see more research on all, not just the methods that didn't work, but all the methods I've applied. Also, can they be applied to other problems, and will it help there as well? Yes. So now some might need to go to the bathroom. I think it's a good time to do it, and we can continue. You're welcome.